Hello guys, today I will be giving a presentation, me and my classmates, over Hooke's Law. My name is Trinity Clavel and my other members are Andrew Austin, Jeremiah Tucker, and Paul Nelly.
Go.
All right, for this first slide, we're talking about Hooke's Law. And Hooke's Law was attributed to launching the modern study of elasticity, which is materials' stress and strain limits and going past their stress and strain limits to break, how they form composite materials, how you know the difference between rubber and something that's more lasting has a breaking point. They basically use Hooke's Law to identify those limits. So there are non-Hookean materials that do not follow Hooke's Law, and the stress-strain relationship is not a straight line. So within Hooke's Law, the stress-strain limit it can be either a straight line or a little bit of a curve, and then it's got a point where it has deformity and breaks. So non-Hookean materials would be like rubber or polymers, anything that stretches and comes to a point where it does not break and then it retains itself. There are several laws that share proportional relationships to Hooke's Law, and that would be Young's modulus, and then there's torsional spring laws, and then there's Ohm's law and Darcy's law, which is fluid motion. So this is just a basic summarization of what Hooke's Law is and how it applies to different fields of study.
Go.
Hooke's Law is the displacement of a spring in which force is applied. F equals the force and K equals the spring constant and X equals the change in the change of X equals the displacement. And to find the spring constant, you just divide by F and switch your K over. For potential energy, it's usually used when you're dropping an object or releasing it, and that tells you how much energy an object is using. And work done is when an object is moving in the same direction as force. So here you have it.
Some applications of Hooke's Law could include various fields of design and engineering that relate to automotive and aerospace engineering, as well as the lesser known fields such as biomedical engineering and seismology.
All right.
Alright, on this slide we have scientists relevant to the creation of this subject, most notably Robert Hooke. As the name law implies, Hooke's Law. You probably could have guessed that one, but he gets most of the credits as he studied this subject heavily. Robert Boyle is also important, as he collaborated with Hooke, and he also had his series of own inventions, such as the vacuum pump. And obviously it's not just a vacuum cleaner like you'd see today. It's, mind you, this is all happening before electricity is commonplace, but stuff like this would evolve into the more common vacuum technologies we see today. Christian Huygens, he helped expand the other two gentlemen's discoveries. Leonhard Euler, these European names tear me up, but he was a genius mathematician, and I believe he's also credited with creating Euler's number as well. And this all goes back to Hooke's creations as he helped popularize them.
Okay, so Hooke studied how elastic materials stretch under force. The process begins by measuring a spring original's length, then recording the elongation under different weights. Plotting force versus displacement produces a straight line, which slope is the spring constant. These experiments revealed how springs behave and illustrate proportional relationships in physics.
Go.
Alright, this slide we discuss some of the difficulties of Hooke's Law. Important thing to remember, as was stated in an earlier slide, this isn't just referring to metal springs like you think of with a slinky or a car shock. Yes, your stereotypical spring sorts. You have to remember this is referring to everything that's elastic. You know, any kind of rubber, nylon. So because of that, you always have that limitation. And you gotta know the maximum of the various materials. If you don't know what that maximum is, that can be a massive setback. Now with modern chemistry and the composition of various modern materials, this helps a lot, but for a material that is just discovered, a lot of assumptions have to be made when studying it.
1.
The original motivation for the experiment that led to the discovery of Hooke's law began with Robert Hooke trying to figure out how to make watches work more efficiently. And he discovered the springs had a stretch limit to the point where they don't fully return back to their shape they originally were, which made him curious to find out what that was.
Okay, so the benefits of discovery. Hooke's law is the representation of spring stiffness to its spring constant, or material stiffness to its spring constant. There's a stress strain that follows the curve of Hooke's law. That's where basically Young's modulus comes into play before the material has its limit and then deforms permanently. Hooke's law is used in a lot of engineering to figure out the elastic limit of concrete, rebar. I mean, anything that you've ever been inside of building-wise or structure has gone through those tests to figure out the material strength, because you want your material strength to be stronger than its limit, so that you don't have a building collapse or fall through the framing. So after the elastic limit, there's basically permanent deformation. That means that whatever material you have will not go back to its original state.
1.
How to set it up? Well, we'll start over.
1.
The modern experiment is set up by having a spring attached to a stable support. A ruler is placed behind it to measure the movement, and known masses are added each one at a time. And how it works, each mass causes the spring to stretch slightly due to gravity. Motion is gently stopped to get an accurate measurement. The position of the spring is recorded each time. And how the data is collected, measurements are based on the precision, not a perfect 0 point. Data shows how the spring changes as more force is added. A linear relationship between force and displacement is observed. This demonstrates Hooke's law in a realistic and practical way.
On this slide, we take a deeper look into the concept of tension. Hooke's law is a linear relation between force and extension. In the isotropic matter, there is no internal material directions defined. It takes the simplest form possible. As you can see in this diagram, this is actually a creation of Young, not Hooke himself, but one of his many followers, I guess we could call them. We can see as it goes down, how the slope goes downward with increased tension, and the effective value just gradually gets smaller.
Hooke's law allows for various areas of life to be made safer and more convenient. For example, it makes the inventions of cars and suspension bridges and car suspension systems, as well as airplanes' wings and other various mechanisms, work and even be possible. Bridges are also made considerably more safe and can also be scaled up to what they were before via suspension bridges.
Go.
All right, this comes to the conclusion of Hooke's law in our group slides, which is the expectations of research discussed. So Hooke's law applies to various fields, including seismology and acoustics. Within seismology, they use wave behavior and support earthquake predictions to give advance warning to people that need it around those areas that are around the ring of fire or anywhere that has any seismic plates that are shifting and causing deadly earthquakes, which we've all seen videos of earthquakes and what they can do as far as tsunamis and after effects. Can kill thousands of people on coastlines within a matter of minutes. So it's great to have a scientific law that applies to making equipment that helps give future predictions. And then within acoustics, basically guides how materials vibrate to shape sound quality. So that would probably be more along the lines of instruments getting the best sound quality. And then lastly, studying past the elastic limit also helps to create a stronger composite materials. Like I said before, any of our structures that we have in society have all had Hooke's law applied to test the limit of the material so that we can make our composite material metals in our buildings stronger, safer, and then apply future materials that may have not even been discovered yet. We can still apply laws that were made in the 16th century or 17th century to today, which is a pretty amazing feat of science to last that long if you have that type of law. All right.